right, start out with any questions. So when we derived Ohm's law, we came up with a formula for resistance and resistivity while we're at it. So the resistance is rho L over A, where rho is the resistivity. L is the length of the wire. And A is the cross-sectional area of the wire. And that black paper that you used for the experiment with the electric field and the electric potential, where you're measuring electric potential, you actually can see this relationship on that just by, you start with a piece of paper, you find what the resistance is, cut the paper in half, find out what the resistance is, and as you cut it in half, well, it depends on which way you cut it, I guess, but if you take long ways and you cut it this way and then found the resistance across that, you basically are cutting the cross-sectional area in half. You should be doubling the resistance. And also, in one of those labs that I don't do anymore just because we had better equipment, but early on I hadn't found some of the equipment that I know we have now, and I had people do resistance experiments with pencil lead. So basically they drew a line on a piece of paper and found the resistance of it. And then in order to double the thickness, they drew a line over top of that, and they got half the resistance because they increased the area by 2. It was just one of those labs that I thought, I can't believe that worked as well as it did. Which is the flip of what I usually think when I on physics labs. So keep that in the back of your mind. We have Kirchhoff's rule. Whether it's a capacitor or resistor, it's something. So the symbol for resistance, if you think about it, resistance is based upon the length of a wire and the cross-sectional area. So if I took a really thin piece of wire, I could increase the resistance, and then depending on how long it is, I could get a specific resistance. And so one thing I could do is just, if I took that wire, coated it so it's not conducting on the outside, and just crumple it into a really tiny space, I create a resistor. And that is the essence behind the resistors we have over here. Oh, there we go. It's just a whole bunch of wire crammed into a small space, or really skinny wire, but it's wire in there. And so the symbol for resistance, or for a resistor, is just as if you took a bunch of wire and crammed it together, and you get the symbol for resistance. Just as capacitor, the essence of a capacitor is you have 2 parallel conductors with something in between, and so you just draw the 2 parallel conductors to represent a capacitor. Have I done I did Kirchhoff's loop rule, right? Voltage rule. I got a nod, so it seems familiar, at least to one of you. All right, 2, we're up to 2. I'm assuming the rest of you are just rejoicing internally that you get to see it again. So I'm going to start at a particular point here, and again, the essence is if I start at a particular point and I end up back at that point, the total potential difference between any point and itself is 0. It's path independent. So I'm going to start here, I'm going to go across my battery, come over here, I'm going to go across the resistor, and then back. So if this is a 10-volt battery here, I'm going to gain 10 volts going from the negative to positive side. So change in voltage, I gain 10 going across the battery, the way I did. I cruise along, come along, and then I go across my resistor here. And then I'm going to end up back at 0. So if I gain 10 going across the battery, I better be losing 10 across the resistor as I go in the direction of current flow. Current's flowing this way. So if I'm going with the current, I've got to be losing potential, and so that puts me back at 0. If I have a 10-volt drop going across here, going in that direction. Now I would apply Ohm's law to figure out what is the current flowing through that resistor. So Ohm's law, delta V is equal to IR. When I'm dealing with current, I'm going to think through the direction. I know current flows from the high end to the low end on the battery, so current's going to be flowing this way. The electron's flowing the other way. So I got 10 is equal to I times whatever my resistance is, and why don't we just make it something like a 5 ohm resistor. So I have 10 volts is equal to I times 5 ohms. And thereby potentially revealing that the SI unit for resistance is an ohm. Named after George Ohm, Georg Ohm. Oh. Sure, we'll go with that. And so we end up with 10 volts divided by 5 ohms. Obviously, the math part is 2. And then the units, volts per ohm is not wrong, but what's the one word unit for current?
Amperes. Oh,
Yeah. Symbol I, yes, the unit's ampere. So that's 2 amperes. Technically, an ampere is defined as, well, actually, an ampere is a coulomb per second. Coulomb officially is defined as an ampere second. For some reason, they made, when things were based upon units, that the ampere was considered the base unit and not the coulomb. I don't know why. All right, in terms of language, I'm fine with amp. 2 amps, 2 amperes, not an issue with me. And I know it should be on a long list of things I just need to get over, but I do not accept amperage as a word. The word is current. Now, out in the field, whatever you're doing, people will use that word, that's fine, but I will not accept it as a word, and when I die, I won't care. So if you can maintain the word, use the word current instead of amperage until I die, I'd be happy with that. Thank you. So if I take my 10 volt battery there, and I got my 5 ohm resistor here, and then I have a 2 ohm resistor here. I know that I have current that's going to be flowing out of the battery. I got a full circuit, current will flow through a full circuit, unless I've got something stopping it. So I got current flowing out here, across there, and then down. There's no place for the current to go. I mean, whatever current's flowing out of here, any current flowing into a spot, got to be flowing out of a spot. So my current flowing across the 5 ohm resistor has to be the same as the current flowing across the 2 ohm resistor. This is in essence what defines a series, as if the current is the same through both. It's in series. So 10 volts and another sad marker. So I'm going to do my Kirchhoff loop. I'm going to start here. Personally, I like starting right before the battery and go across. I like the first term to be positive. That's just me. Not everyone does that. If you like the first term to be negative, sure, why not? But I'm going to start here. I'm going to go across the battery. So I got 10 volts. I'm going across my 5 ohm resistor. Well, I know that I'm going to lose something there. I don't know how much yet officially. But I know that whatever my loss is obeys Ohm's law. So it is, my voltage drop here is I times R. So minus 5I. Minus 2I is equal to, and then back to where I started. This is the change in voltage across the 5 ohm resistor, the change in potential across the 5 ohm, the change in potential across the 2 ohm resistor. So I have 10 is equal to 7I. So if I think about it in terms, again, Ohm's law, I got 10 volts dropping across both resistors. So this would be the loss across both resistors, or an equivalent resistance is equal to R times I. My equivalent resistance is 7. Or generalizing it, if I had just done generic R1 and R2, for resistors in series, my equivalent resistance, sure inside series, is just the sum of them, however many I have. Please do not confuse us with capacitors, where capacitors in parallel add this way. Resistors in series add just by straight up adding them. Now, it makes sense that this would be the case, because in order to create a resistor, all I need is a length of wire. Now, typically, the wires, the banana plug wires that we have over there, we assume the resistance is minimal. However, there is a lab that usually comes out with pretty decent results. Where you have a very thin wire right here, and you can actually measure a difference in resistance depending on how much length you take of it. And in that particular lab, then based upon the resistivity, you can go to a table and figure out what material that is. But if I just have a long wire right here, it has a certain resistance based upon that formula right there. If I know the material and I know the cross-sectional area, which I can find easily enough with a micrometer, I can find the diameter and then do some math. So I treat this whole thing as some resistor R. And now I just, instead of looking at it as one long piece of wire, I'm going to look at it as two shorter pieces of wire. So I'm just arbitrarily pick that spot. I'm going to call this my resistor 1 and this my resistor 2. Break it into 3 or 4, or however many that you want. But indeed, whatever current I have flowing into the wire there has to be flowing out this way. There's nowhere else for it to go. And so R has to be equal to R1 plus R2, or rho L over A is equal to rho L1 over A plus rho L2 over A. So L, the full length here, if that's equal to L1 plus L2, well, just more support for this idea that resistors in series just add up. Obviously, parallel, it's going to be the other one. So let's actually show that why adding up resistors in parallel will get you, you'll be doing, adding up reciprocals and then taking a reciprocal of that. Questions before I do the parallel? Sure, we'll make it 10 volts and 3 ohms. What did I do before? I did 5 and 2, so we'll make that 2. I know these are in parallel because if I look at each side of it, there is a junction before each of them and a junction right after and nothing else in between. So I've got 2 junctions and resistor, 2 different paths. They are in parallel. I know I'm going to have a current flowing out of my battery here, going off to the right, comes up to here and comes to a junction. So why don't I just make this current I, and now the current's going to split. Most of it will go the path of less resistance, so more of it's going to go across the 2 ohm resistor than the 5 ohm resistor. So I've got, we'll just call this I2 going this way and call this one I5 going that way. They will join up again at the other junction, but we've established here that I is equal to I5 plus I2. And this is Kirchhoff's junction rule. whatever current you have flowing into a junction has to equal the total current flowing out of a junction. And then on the other side, I've got I5 and I2 coming in, and that has to add up to what comes out, so I have I coming out of it. All right, so let's go through, and I know that from this right here, if I could find my equivalent resistance for these two resistors right here, that I would have, one question I'm asking is, I guess, what equivalent resistance would I need here in order to get this amount of current flowing out of my power supply? So I'm just going to call it Req. Again, Ohm's law, delta V equals IR. If that's my equivalent resistance, this is the current flowing out of the power supply. And so I is equal to delta V over R. So I have, from that over there, I've got delta V of the power supply divided by my equivalent resistance is equal to I5, the current flowing across here, which better be the voltage across my 5 ohm resistor divided by my 5 ohm resistance, plus delta V 2 over R2. Now in this particular situation here, my voltages are actually all the same. I can treat that whole thing as a junction and that whole thing as a junction. Going from one side to the other, I have 3 different paths I can go through, and it's got to be the same voltage when I go from any spot to the same spot on the other side. So all my voltages are the same, and so I have 1 over my equivalent resistance is equal to 1 over the first resistor plus 1 over the second resistor. So in this particular case, that would be 1/5 plus 1/2. And so my equivalent resistance is 10/7 ohms. Give you a moment to let that sink in, then I'm going to ask a conceptual question. So do note that my equivalent resistance is less than the smaller resistor, and that should always be the case. Unless somehow they came up with something called negative resistance. Not sure how that would work, but I'm sure there's a theorist around there somewhere who's come up with some way to make that work. All right, so, but then I started out with just the 5 ohm resistor, which was the first case I did that I've erased. And now I'm dropping the overall resistance by adding a resistor. How does that make any sense? So if I started out with just that, I got 5 ohms of resistance, I add a resistor, and suddenly my total resistance is less. Why does adding a resistor cause a drop in resistance?
There's more area.
Yeah, I guess that would work. I was thinking slightly different wording, but I guess looking at that formula right there. Yeah. I was thinking the analogy that I typically do is if there's a fire in this room and we all bolted for the door, there are only a certain number of us who can get through that door at once. So how thin the door is affects how easily we can get out. Sort of, in some sense, that's a resistance right there. If we open up that door, even if it opened up just a little bit, as long as one person can get through that door and the rest of us can get through this door, then we get out of the room faster. Us being the charges, how fast we get out deals with the current that's flowing. So instead of thinking of it as I've added a resistor, is without that there's infinite resistance there. What I've done is I've changed the resistance from infinity to something more manageable. So open up a second pathway, increase the area, either way you wanna look at it. It's something similar with the 152 class, and somebody got an answer almost immediately as well there too. And I've done that question for a number of years, and this is the first year, it was in both classes, but the first year that people got it pretty much right away. I'm wondering what I did differently. Well, I'm glad it, whatever happened, maybe it's just more brilliant students. That's
Not right here.
all right, so let's run through a couple of drills here, and then we'll get more and more complicated as we go. 12 volts and a 3 resistor. What is the current flowing out of the battery? Yep. I gain 12 volts here, I lose 12 volts here. The resistance is what's limiting the current. So what matters is what is the voltage here. That's, I lose 12 volts there. So I got 12 divided by 3 is 4. So I have 4 amperes flowing out. And no, we'll make it the same for right now. What's the current flowing out of the battery now?
2 amps.
We double the resistance, we cut the current in half.